Welcome, everyone. In this next lesson, we're going to see how derivatives actually come into these and relate to these characteristics of graphs that we've been looking at. And specifically, we're going to see how the first derivative and the second derivative are related to this idea of our function being increasing, decreasing, and concave up, concave down. So let's start with the first derivative. And we have what's called the first derivative rule. And what this tells us is that if our first derivative is greater than 0, then our function is increasing at this x value, x equals a. And if the first derivative is less than 0, well, then our function is decreasing at that spot. So really what this tells us, to kind of summarize, is that if f prime is positive, then the original function f is increasing. And if f prime is negative, so if our first derivative is negative, well, then the original function is decreasing. And this is going to be a relationship that we're going to kind of refer back to over and over. So this one's pretty important. So if our first derivative is positive, the original function then is increasing. And if the first derivative is negative, then the original function is decreasing. And so why is this? Well, let's see what it means for the first derivative to be positive, to be greater than 0. Well, we remember the derivative, what this derivative value represents, this tells us that the slope of the tangent line is positive at this location, at x equals a. And so the fact that our slope is positive, well, that tells us our graph has a very specific shape. If the tangent line has a positive slope, well, then what our graph would look like is the tangent line would be moving up. And so then our curve would have to be moving up as well at that point of tangency. And we can see that if it's kind of moving upward, has this positive slope, well, then it must be increasing. And the same goes for negative. So if f prime is less than 0, well, what that means then is that the slope of our tangent line is negative. At this x equals a value. And so if we have positive slope, this is what our tangent line would look like. And if we have a negative slope, well, it's going to be going in the opposite direction. So if we have negative slope, we'd have something that looks like this. And as an example for what our curve would look like, well, maybe it looks something like this. And we see that it's decreasing. So our first derivative really relates to how our function, the general trend of our function, is the function moving up? Is it increasing, or is it moving down? Is it decreasing? And so let's try an example where we kind of put all these pieces together. So in this example, we're going to sketch the graph of the function, and we're given 4 different properties here that we're going to kind of investigate. So let's look at the first one. F of 3 is equal to 4. So what this actually tells us is this tells us something about the original function. So this actually tells us that the point 3, 4 is on the graph. Of our function. So again, when we look at this, the value that we're plugging in, this is the x coordinate, and the value that we get out, that's the y coordinate for our point. So let's actually plot this. So we want to plot the point 3, 4. So we find x is equal to 3, we find y is equal to 4, and then we find the point on the graph. And let me do this in, here we go. So we know that point is on our curve. All right, so what other properties do we have? Let's look at the next one. So this next one tells us that the derivative at 3 is equal to 0. So what this means is if our derivative is 0 at this x value, then we must have a horizontal tangent line, must be flat. So we have a horizontal tangent at x equals 3. All right, so let's just sketch that in just to help remind us. So at this point, we're going to have a horizontal tangent line. So our curve is going to have to flatten out, essentially, right there at x equals 3. All right, so let's look at the next couple properties. And these are ones about the first derivative and about the sign of the first derivative. So if our first derivative is positive, well, our first derivative is positive when x is less than 3. All right, so what this is really telling us, if we kind of go back to our first derivative rule, is that if f prime is positive, well, then really this is telling us that the original function f is increasing for this interval x less than 3. And if we look at the other property, this first derivative is negative for x greater than 3. So really what this is telling us is that f of x is decreasing when x is bigger than 3. All right, so let's look at our x-axis here, and let's record this information just to keep track of. So we know something's going on at x equals 3. So let's plot that along the x-axis just to keep that in mind. And from that third property, we know that when x is less than 3, our function's increasing. So x less than 3 is this section of the x-axis. And then x greater than 3, well, that's this section of the x-axis. And so what we found is that on that left side, our function is increasing. And then on the other side, our function is going to be decreasing. And what has to happen is on this side, our function has to be, on this left side, our function has to be moving up. On this right side, our function has to be moving down. And then where it changes over, our graph has to flatten out temporarily. And so how this would have to look is something like this. Maybe it's symmetric, maybe it's not. But we're just looking for a graph that satisfies these conditions. So if we look at this, yep, our graph is moving up. Then it flattens out momentarily right there. We have a horizontal tangent. And then it starts decreasing. And that point is on our graph. So it satisfies, so this is an example of something that satisfies all 4 of those properties. Now there's other graphs that would also work. So, something like, maybe it's something like this, or maybe it's not so symmetric. Maybe it's something like that. So there's a lot of possible choices here. This is just one example of what our function would look like that satisfies all three of these properties. All right, let's see about the second derivative now. So the second derivative tells us about the shape of the graph. It tells us whether our graph is concave up or concave down. And so we have a similar property or similar rule as the first derivative rule. And what this one says is that if our second derivative is positive, then the original function is concave up at that x value. And if our second derivative is negative, then the original function is concave down. So to kind of summarize this, if the second derivative is positive, well then the original function f is concave up. And if our second derivative is negative, then the original function f is concave down. And so this is very similar to the property for the rule for increasing, decreasing, except now we're talking about the second derivative, and it's telling us about the shape of the graph, the concavity. And so why this rule works is, let's think about it for positive here. So if the second derivative is positive, what that really means is that our first derivative is increasing. And if our first derivative is increasing, what that means is the slope of our graph is increasing. And if the slope of our graph is increasing, well, that's precisely what it means to be concave up. And so there's something similar for if the second derivative is negative. So if the second derivative is negative, well, what that means is then the first derivative is decreasing. And why this is true is what we're doing here, going from this step to this step over here, or this step to this step over here, we're applying the first derivative rule, but now we're applying it to the second and first derivatives. So this is almost like the rule we just looked at that tells us if a derivative is positive, well then the original function is increasing. So now we're kind of doing it on kind of one level up when we're looking at this. And so if our second derivative is negative, that means the first derivative is decreasing, which means the slope of our graph, the slopes, are decreasing. And if our slopes are decreasing, well, that's precisely what it means to be concave down. And so when we think about a graph, there's really two choices. For most points, there's two main choices for whether our function is what our function's doing. So there's the possibility that our function is increasing, and there's a possibility that our function is decreasing. And so if our function's increasing, the general trend of our function is up. It's moving upward. So the tangent line would be moving upward. It'd have a positive slope. And so then relating this to the concave up and concave down, concave up would bend above the tangent line, and concave down would bend below the tangent line. And then something similar for a decreasing function. So if we had a decreasing function, well, that means our tangent line would be kind of moving downward. And there's two options for a decreasing function in terms of concavity. The curve could either bend above it, in which case it would be concave up, or it could bend below the tangent line, in which case it would be concave down. And so this is how you can kind of remember there's really four main options for how our curve can look. It can be increasing and concave up, it can be increasing and concave down, or it can be decreasing and concave up, or decreasing and concave down. And you can think of it as like our tangent line and then how the curve actually bends around that tangent line. Does it bend above? So we have our tangent line here. If it bends above the tangent line, it's concave up. If it bends below the tangent line, it's concave down. And then same thing for decreasing. So let's try an example where we kind of go through a bunch of properties again and try to put all the information together and sketch what a graph might look like. You know, there's going to be many different graphs that satisfy these conditions, but let's just sketch what one might look like. And so let's start with the first property here. And what we're given is three pieces of information about our function. And what these tell us specific points that are on the graph. So, for instance, this first function value, f of 1 equal to 2, this tells us that 1, 2 is on the graph of our function. The second one here tells us that 2, 3 is on the graph. And then this last one tells us that 3, 4 is on the graph. So again, the x-coordinate is the number that we're plugging into the function, and the y-coordinate is the number that we're getting out. So let's plot these 3 points on our graph. So 1, 2 is right around there. 2, 3 is right around there. And then 3, 4 is right there. So we have those 3 points. All right, so what other information are we given? Well, the second property here tells us about the first derivative at x equals 1 and at x equals 3. So at those two places, the derivative is equal to 0. So what that means is we're going to have a horizontal tangent line at those two x values. So we have a horizontal tangent at x equals 1 and x equals 3. So we have it at both of those places. So let's just draw in our little horizontal tangent lines at x equals 1, just to remind us that our graph is going to flatten out there. And then again at x equals 3, let's just draw a little bit of the tangent line in, just to remind us that our graph is going to flatten out there. All right. So then let's go down to the last two properties. These are the ones that tell us about the sign of the second derivative. So what we're seeing is that when x is less than 2, the second derivative here is positive. So if our second derivative is positive, that tells us then that the original function f is concave up for x less than 2. And the last property tells us that the first derivative is, I think this is a typo here in the notes. This should be the second derivative. Yeah. So that was the first derivative. But I think this one should be the second derivative there. And if that's our second derivative, then if our second derivative is negative, that means the graph is concave down. So that tells us that f is concave down for x greater than 2. And so what's happening is we see that our kind of the behavior of our function is getting split up right around this x equals 2. And we also have this third property that tells us that the second derivative at x equals 2 is 0. And so when that happens, it tells us we have a possible inflection point. Now, for it to be a true inflection point, though, we also need to check. There has to be a switch in concavity. So we'll keep track of that, but we are going to have a switch in concavity here because we see that right around x equals 2, a little bit to the left, our graph is concave up. A little bit to the right, our graph is going to be concave down. And then we're switching right at x equals 2. So we are going to have an inflection point. So now let's kind of keep track of this. And we know that something's happening at x equals 2. So let's kind of plot that along our x-axis. And we know that for x less than 2, the graph was concave up. So let's record that here. So on this side, we're concave up. And then on the other side, for x bigger than 2, this is where our graph was going to be concave down. And so let's draw in what the concave up shape looks like. So we're going to have something that looks like this. And then let's draw in the concave down shape. We're going to have something like this. And then let's just kind of finish it off. So we're going to have an inflection point right there at x equals 2. And then we can just kind of keep the graph going here in either direction. And here we have a sketch of a graph. Now, this isn't the only graph that satisfies these conditions. But what do we have? Well, we have these 3 points, which was the first property. Our graph flattens out at x equals 1 and x equals 3. So we have a horizontal tangent line. That was the second property. And then we were concave up for x less than 2. So when x is less than 2, we have that concave up shape on our graph. And then when x was bigger than 2, we're concave down. So we have that concave down shape. And then right there in the middle, at x equals 2, that's where we actually change, the shape of the graph changes. And so as we're looking at this, we notice that as we drew this, our graph has a relative min at x equals 1 and a relative max at x equals 3. And this is not coincidence. This is what we're going to see always has to happen if so we have a relative min at x equals 1. And the reason is because f prime of 1 is equal to 0, and the second derivative was positive there. And this is going to be true for any x value. If the first derivative at an x value is 0 and the second derivative is positive, well, then we're going to have a relative min. And then same goes for a relative max. We have a relative max at x equals 3 here, or a local max if we want to call it a local max. And that's because the first derivative at 3 was 0, and the second derivative at 3 was negative. It was less than 0. And so this is going to be true in general, that if our function has the derivative equal to 0 at an x value, so we have a horizontal tangent line and we're concave down, well then we're kind of forced, the graph is forced to have a relative max. So if we have a horizontal tangent line and we're concave down there, it's going to be a max. Just like if we have a horizontal tangent line and we're concave up, it's going to have to be a min. And this is something that we're going to see in a little bit. All right, so I think we'll stop there. And what we'll be doing in class is we'll continue on with the next example. And in this next example, we're going to see we're given a function. So we're given a function f of x, and we're going to see how to actually sketch what the graph of the derivative function would look like based on knowing information about some of the different slopes. All right, so we'll see you then. Bye-bye.